In this last section in Chapter 6, we're going to look at how to analyze paired data through the process of a hypothesis test. Now, we can analyze paired data by performing a hypothesis test for a mean difference. When we do this, our null hypothesis is going to assume that there is no difference between two treatments in our experiment, or that a variable's measurement before is equal to the variable's measurement after. And remember, we talked earlier about how there are two ways to set up data in a paired experiment, and one could be a before and after situation. Now, the example that we're going to look at here involves the case where Major League Baseball began testing its players for the use of steroids and other performance enhancing drugs. They actually began testing in 2004, but it took a couple of years for them to begin punishing players caught using them. And even though before 2004, steroids technically were illegal, many players, it's believed, used them because there weren't really any punishments if they got caught. Now, as evidence that players were using performance enhancing drugs prior to the testing, a lot of people looked at home run data as an indicator of this. And later on in this course, we'll be looking at home run records over and how those have changed over the course of time. But in the late 1900s and early 2000s, all of a sudden there was a really big increase in the number of home runs that players were hitting on average in Major League Baseball. Now, if we assume that steroids did have an effect on the number of home runs, we would expect the number of home runs to decrease if many players were using steroids and then stopped using them once testing began. So, to investigate this, we're going to look at the difference in the number of home runs hit by teams in 2006 and 2008. So, in your notes, you have a chart that is giving some information about baseball teams and the number of home runs that players hit on each of those teams during these 2 years. And the reason we're looking at 2006 and 2008 is because 2006 was an earlier date, and that was right after they started testing for steroids, and they really hadn't started enforcing penalties at that point. So many people believe that a lot of players were still using performance enhancing drugs at that point. But by 2008, they had really started to come down on players and enforce penalties. And so, what we want to know is, was there a difference in the number of home runs hit, and how significant was that difference? So, your chart is set up 2006, 2008, sort of before and after. And notice that in the difference column, we are subtracting 2008 minus 2006. Now, the reason we're doing it that way is because that way, if we come up with a negative difference, like we did in this first year here, a negative difference indicates a decrease. So notice here the number of home runs hit by the Diamondbacks went down by one, and that's why we have a negative here. Look at the Braves, however. They have a negative difference of 92 home runs. That means they hit 92 fewer home runs in 2008 than they did in 2006, which seems to be a pretty big difference. However, we also had a couple of teams where their number of home runs went up, right? Like the Rockies went up by 3, the Marlins went up by 26. And then we had the Angels where there was no difference in the number of home runs that they hit. So, kind of results all over the place. And we need to analyze this data and see if there, first of all, if there is a difference, and then also if it's significant. So, the first thing you would want to do, of course, is fill in the rest of your chart. And since we did most of them for you, you can probably just do the rest by hand, and that would be quicker than doing it in your calculator. So, I'm going to go ahead and calculate those differences. And again, pay attention to the order. We're doing 2008 minus 2006. So we completed the table. Now, part B asks how many teams had an increase in the number of home runs from 2006 to 2008. If we go back and look, there were 7. There was only one team that had no change in the number of home runs, and therefore we had 22 teams out of the 30 that had a decrease in the number of home runs. So that seems like it would be pretty good evidence, but we'll continue on with our hypothesis test. So, first thing we're going to do is write our hypotheses. Our null hypothesis is that Major League Baseball teams had the same ability to hit home runs in 2008 as they did in 2006. So, our null hypothesis, again, always assuming no difference in ability. Our alternative then is that the teams in the MLB had less ability to hit home runs in 2008 than in 2006. Now we're going to calculate our test statistic. And because we're using paired data in this example, we're going to use the mean difference in the number of home runs hit. So we would take those differences, the -1, the -92, the 8, and so on, and we could add all those up and divide by 30, or we could put them into the list in our calculator. Anyway, we come up with a mean difference of -16.93. That's a pretty big negative difference. And now in your notes, you have a dot plot, which is showing 100 trials of a simulation that were conducted, assuming that there's no difference in ability of teams to hit home runs. And notice that because we're assuming there's no difference in their ability, most of our results are pretty close to zero, right? So zero would mean no difference. We have some over here that are on the positive side, positive meaning that their number of home runs actually would go up from 2006 to 2008. Here we have some going down. So sort of symmetric around zero, which is what we would expect if there was no difference. But we want to now look at our results, right? We had a difference of negative 16.93. Notice that in our simulation, none of the results came up with a difference that was as large as negative 16.93. So our p-value in this case would be zero, right? We had no values in that range over there. So our p-value was 0%, and that means we have very strong evidence that there is a difference. So we would reject our null hypothesis. We would say that there is good evidence that teams have less ability to hit home runs in 2008 than they did in 2006. In other words, the testing for steroids really did seem to make a difference, and we probably have good evidence that many players were using steroids before the testing started. Now, at this point, I'd kind of like to pause from your notes and kind of show you the applet that I use to make the dot plot that's given in your notes. And you will be provided with a link to this, but this is the applet for the mean difference. And notice it says they're paired data. So the way that you enter the data is that you have to enter the observed differences in each context below, separated either by commas or spaces. So what I did is I went back and I typed in the difference for each team. So I have -1 for the Diamondbacks, -92 for the Braves, and so on. So you actually have to calculate those differences before you can put them in the applet. Now, if you click on this button that says calculate observed mean differences, it will calculate the mean difference for you. So we got -16.933, which is the same thing that we got when we did it by hand. It just went out to more decimal places. And like we've done in the past, you would probably type in that you want to simulate 100 mean differences. Usually we do 100 just because it makes the p-value calculations a little bit easier. And then when you click the add more trials button, you'll get your dot plot. Now, when I did the simulation here, this is a little bit different than the one that's in your notes. Notice I actually had a couple of simulations that went below -12, but still the smallest was still greater than -15. So you can use the applet to count the number of dots that are less than or equal to your test statistic. So I typed in the -16.93 here and clicked count, and it told me that 0 of my simulations were less than that value. So that agrees with the same p-value that we got from the dot plot that's in your notes. We're going to look again at our Olympic speed skating data that we looked at in an earlier example in this chapter. Remember, we talked about how when the speed skaters skate in pairs, one skater starts in the inner lane and the other starts in the outer lane, and they switch partway through to make sure that they're all skating the same distance. And when we did this example earlier, we found that there was a positive difference in those times, meaning that the skater in one of the lanes had an advantage over the other by close to a half a second. But now we want to analyze this data and see if that difference is significant. So in this case, we know that this is paired data because the skaters race against each other in pairs, and we have two skaters that are racing at the same time. Because they are skating in pairs, we would analyze this as a mean difference. And earlier in the chapter, we calculated that value as 0.499 seconds. Now, if you didn't remember that, you could do it again pretty quickly with your calculator, but we did that earlier in the chapter. So that 0.499 seconds then essentially is going to be our test statistic. And remember that the positive difference of 0.499 seconds indicated that skaters that started in the inner lane are slower by an average of 0.499 seconds. Now, if we write our hypotheses that we're interested in testing, our null hypothesis would be that the skater that starts in the inside and outside lanes have the same ability to win the race. And that's what we kind of hope would be the case because, after all, if we're doing this in the Olympics, we want everything to be fair and we don't want there to be an advantage to one skater over the other. Our alternative then is that the skater that starts in the outside lane has a greater ability to win than the skaters that start in the inside lane. And the reason we're wording it that way is because our test statistic was positive, indicating that the skater on the inner lane was slower by about half a second. And that would mean that the skater in the outside lane would have a greater ability to win. Now, I gave you the dot plot here showing the simulations, and remember our test statistic 0.499. So we have to kind of use our best ability to kind of guess where 0.499 is. But in the one in your notes, you have a very faint dashed line in here, kind of indicating where that value is. It might be a little bit hard to see. But anyway, if we look at this and we kind of even estimate about where zero point 0.5 is, we can see that there are a lot more than 5 dots here, right? So regardless of whether we count up there, like when I counted, I got 16 dots, maybe you get 15, depending on where you think the 0.499 is located. Either way, that value is above 5%. And that would lead us to the same conclusion, which is that we would fail to reject our null hypothesis. And that's what we probably would hope would happen in this case, because failing to reject the null hypothesis means that there is not good evidence that the skaters who start in the outside lane have a greater ability to win. In other words, we've proven that the race is basically fair, and no matter where you start, inner or outer lane, you're going to have the same ability to win the race. Please do homework 6.3 in your assignment packet.